Alrighty, so looking at our Pythagorean theorem, remember that this is the sum of the squares of both sides. So I have a leg and I've got to square it. Got another leg B, I've got to square it. I've got my hypotenuse C and I've got to square it where A and B are those legs like I just said, and C is again that hypotenuse. Okay. Now remember that hypotenuse is across from that right angle. It's not touching. When I say across, I mean not touching. And so if we're going to use this Pythagorean theorem, we need to be able to say, okay, these are the legs. This is the hypotenuse. And again, I just said that it was the side across from the right angles. Um, and when that is true, if it's across from those right angles, it's always going to be the biggest side, which is helpful to remember. So in this situation here, the word we're looking for again is across, which means again uh, not touching. So when I say across, I mean not touching. And again, that is going to be the hypotenuse, which I'll just probably write the word hype. And then our legs are going to be A and B here. Okay. It could have been B, then A. It doesn't matter for those legs there. Um, so again, it is important to remember that this only works for right triangles. So if you have a situation like this, if you've got like 60, 45, and oh, this is embarrassing. I think 75, 75, this would not work. We cannot use the Pythagorean theorem for this works, for that situation there. It only is for those right triangles. So in this case, x, let's say, is that the hypotenuse or a leg? Well, it's across from, it's not touching that right angle. So we call that the hype. And again, that's the letter C. I usually make the smaller one my A, but it's really up to you. It does not matter. So B is going to be 6. So if I'm showing all my work here, I've got A squared. If my thing doesn't lag, got my equation there. Then I'll put 3 to the second power. I'm just replacing stuff. Plus 6 to the second power equals c squared. All right. Now, a common mistake that can happen is people do 9 to the second power, but order of operations tells us we've got to square these first. So that becomes 9 plus 36 equals c squared, and then 45 equals c squared. Now, in your previous classes, you might have just square rooted both sides and gotten a decimal, and that is fine. Again, the square root button is right here. You would press 45 and then take the square root. It's going to be 6.71 ish, but we want to be as precise as possible here. So there is a way to break down that 45, radical 45, and not get a decimal. So a helpful thing to have handy is all of the perfect squares. So 2 squared is 4, 9 is 3 squared, 16 is 4, 25 is 5, 36, 49. I'm going to write a bunch more and then pause it. This list goes on forever. So I would say probably these first 5-ish are going to be our best friends when we're working with these kinds of questions. So I want to ask myself, can any perfect square divide 45? Okay, that's the question. That's what we're looking at here. Well, I usually start. You want to find the biggest one, but sometimes I start with the smallest in the beginning, just so we understand what's happening. I can rewrite that as 45 is the same as 9 times 5. 9 times 5 there. Okay. Now, you might be saying, "What are you doing, man?" Well, the square root of 9 is 3. So I'm going to put 3 outside of that radical. I can't take the square root of 5. I also can't divide anything else. Nothing else can divide 5. So my final answer is going to be 3 radical 5. So that hypotenuse, that x equals 3 times radical 5. Okay. Again, you can get a decimal, but we want to get in the habit of doing radicals. Boom, another radical pops up right here. This is a 45, 45, and then 90 degrees. Well, I've got two congruent angles down there, so I can actually put X right there as well. Um, this is an isosceles triangle situation. That's a good thing to remember. Spelled that wrong for a second. Isosceles. The different spellings we get for that is like so incredible. All right, so we start with our a squared plus b squared equals c squared. All right, so this is kind of a harder situation. I wanted to throw this in here. So both of those legs are x, and that's what we're trying to find. And so I'm going to do x squared plus x squared equals 12 radical 2 squared. All right, so that might look a little tricky, but remember, we just square everything. I'm going to start with the right side here. I do 12 to the second power, which is 144, times radical 2 to the second power, which is just 2. Okay, so yeah, then I combine my like terms over here. Remember, you've got a 1 out in front here. So this is the same thing as 2x squared. 2x squared. And now I just got to solve for x. Well, I'm multiplying everything by 2. So I actually want to divide everything by 2. And I get x squared equals 144. And a lot of times our stuff's going to work out, which is really nice. We won't have to get that nasty 3 radical 5 stuff. If you take the square root of x, you get, sorry, the square root of 144, you get 12. Okay, so my legs in that situation, they're both going to be 12. Now, 15 blank 17, I've got a squared, b squared equals c squared. Remember, the 17 is that hypotenuse. It's across from, it's not touching that right angle. 15 is a leg, x is a leg. So I'm going to do x squared plus 15 squared equals 17 squared. That gives me x squared plus 225, I believe. And 17 squared, 17 times 17 is 289. Alrighty. So that gives me x squared equals, I've got to subtract 225 from both sides. And I get x squared equals, is that 4 and then 6, 64. Taking that square to both sides. Use your calculator. Why would you not? Obviously, it's helpful if we memorize, but we've got a calculator always with us. So that gives me an 8. So none of that wild 3 radical 5 stuff happening. Pretty simple one this time. 8, 15, 17. So notice those are all whole numbers, 8, 15, and 17. That doesn't happen super often. When 3 whole numbers satisfy the Pythagorean theorem, we call that a Pythagorean triple. Okay. The smallest one we said the other day was 3, 4, 5 because 3 squared plus 4 squared equals 5 squared. You can check that with 9 plus 16 equals 25. Um, this is useful, typo there, because if you find the Pythagorean triple, then any multiple, so you can multiply it by 7, you can multiply it by 11, you can multiply it by zero point 0.2, doesn't matter, any multiple, there's an I in there, any multiple of those 3 numbers is going to work for our Pythagorean theorem. So we said 3, 4, 5 the other day. We also talked about 5, comma 12, comma 13. And then another helpful one that comes up, our third in my opinion, most common Pythagorean triple is going to be 8, 15, 17. So, what's the relationship here? If I multiply by 2, that gives me a 6, 8, 10. Multiplying by 3, that gives me a 9, 12, 15. And I can multiply any of these by 5. I can multiply this by 5. I can multiply that by 5. It still would work. But I'm just multiplying the original, and I get 15, 20, 25 there. Okay, so again, same thing, same concept over here. If we multiply the side lengths, we should notice that all of these triangles are similar. Okay, that's from the last unit. All these triangles are similar, which again means congruent angles and proportional sides. Alrighty, so hopefully this is making some sense and we are tracking along. Appreciate you guys.